All right, let's take a look here at the last example from this section. Suppose that G is a simple solid region in R3, and let sigma be the boundary of that surface. And we'll assume that that surface is given a positive orientation. So again, if sigma is the boundary of a boundary surface of G and G is a solid, then it's got to be the case here that sigma is a closed surface. It encloses a solid. So suppose that you are told that G has a total volume of 10. We don't know what G looks like, but its total volume is 10. If an object of constant density occupies the region G, then prove that 1/20th times this double integral is the x-coordinate for the center of mass of the solid. Oh gosh, okay, so this again is bringing together a lot of ideas that we have seen in previous sections. Let's start with at least this idea of the center of mass that's brought up here, and this concept of density. So let's suppose that the density, or the density function rather, for the object is rho of x comma y comma z. This is what we did back in 4.8. But notice here that we said that there's supposed to be a constant density. So let's just say I don't know what that constant density is, but we'll give it the value of c, some constant c. Okay, so now we can pull back on our 4.8 knowledge and just say that by definition, the mass of the solid is given by, okay, so this would have to be a triple integral over G, and remember that we would just use our density function, dV. Okay, now what we can go ahead and actually try to do here is to see what we can understand from this. So, our mass, which is equal to this triple integral, can be updated a little bit because we know that the density itself is just some constant. But of course, if c is just a constant, we can take it outside of the triple integral. And if I look then at the triple integral that's left, what does this triple integral represent? Well, yeah, again, it represents the volume of G. And in the question, weren't we told the volume of G? Yeah, we were told that G has a volume of 10. So ultimately, this is going to be 10c. The mass of this thing is 10c. Well, now if I want to show that this integral is the x-coordinate for the center of mass, why don't we just try to find what the x-coordinate is? So I'll say down here, we know that to find the x-coordinate for my center of mass, I have to do 1 over the mass, and I have to multiply by the triple integral over G of x times my density. Okay, so let's try to simplify this with some of the pieces that we know. Well, first off, we know that the mass is 10c, so we can put 1 over 10c at the start. We know that our density is just c itself, so we can set up this. Of course, this means here that we can go ahead and cancel out this value of c that's going to be in the top and the bottom of the resulting fraction. And so we're ultimately just going to have 1/10 times a triple integral over G of x dV. Now we can try to see how close we are to maybe what we're trying to get to. Right now I have a triple integral representing the x bar, that is the x-coordinate for the center of mass. But I'd really like to show that it's equivalent to this. Okay, well again, by the divergence theorem, I might be able to go ahead and start to bridge some connections between this double integral, that's measuring something like a flux, and this triple integral. Before I do that though, I'm going to make one small observation. I notice that I need a fraction out front of 1/20th, and here I only have 1/10. So I'm going to quickly go ahead and just say I could make that fraction out front a 1/20th, as long as I, of course, multiplied what's on the inside by a 2. So this now is getting a little bit closer to what we have. If I can now show that this double integral is the same as the triple integral. So let's see. I'll pause here. And I'll say, well, actually, how about we don't pause, but we'll just continue on. We're almost out of space. One thing that I might notice is that 2x has a very, very interesting relationship to the actual vector field that's listed here. You might notice, if I was to try to look at the divergence for this vector field, what does the divergence for this vector field come out as? Well, let's see. It would be 0. Partial with respect to y is x. Partial with respect to z is x. So the divergence is 2x. So this here is actually the same as saying the triple integral of the divergence. But of course, by the divergence theorem, we know that we can kind of continue what we have here and say that this should be 1/20th times, and we should be able to immediately say that this is the same as the flux integral that's over sigma. That's going to be our vector field dotted with, remember this would be n dot ds, but of course that's exactly the same as just stating ds, where s is a vector. So we were actually able to show the x-coordinate to the center of mass has exactly this formula here. Just got to remember to write in that 1/20th. Okay, so we'll see a lot of different ways where sometimes this divergence theorem can be used as like a tool to help us justify certain facts. And so we should always keep that in mind. Whenever we ultimately have a triple integral, we know there's a connection kind of back to some other flux integral that we might be able to work with. So one final fact before we end this section is that the divergence theorem actually also holds for regions which are finite unions of simple solid regions. So proving this fact is very similar to proving that Green's theorem was going to work for regions that contained holes. So you might recall we did some questions like that where like, does Green's theorem work if I have a region D that looks like this donut shape? And we said, yes, it does. And so we can imagine maybe the same sort of thing here. What if I had something like a sphere, but it had, some sort of a hole burrowed in it somewhere, right? Like there was some gap that went all the way through there and all the way out the other end. Does this still work? And we could actually say, yes, it does. We won't see that fact a lot, but it is an interesting extension of the idea and aligns very, very nicely with what we've seen about Green's theorem. The section here of 5.7 is a rather complicated one, at least at first glance, and it will take some getting used to. I'm going to highly encourage you to make sure you go to those worksheets and really try to practice the ideas that are there. On the upcoming exam, you will be asked questions that are going to ask you to understand not only how to use the divergence theorem, but also how to go ahead and deal with calculating flux directly. In fact, on the worksheets and on the homeworks, I have questions like this, where I say, hey, use the divergence theorem to find the flux through this, but also compute the flux directly by dealing with the two separate sides. And on the exam, I love to ask questions like that as well. So it's definitely a good thing to go try to practice with those worksheets so you feel extremely well prepared.